welcome to This is Lady Ada.
Hey everybody, it's me, Lady Ada, and it's my desk where I'm going to be doing some engineering tonight. Last night we did Sunday Ham, that was great, talked about Tytera MD380 and showed how to do some more programming for the code plug on that radio. Today we're also going to be doing radios, but of a different variety. Rather than the 400-ish megahertz radios that I was showing last night, tonight we're going to be talking about 2.4 gigahertz radios. This is a 802.15.4 compliant radio transceiver with a microcontroller built into it. So all the way on the other end of like very structured data, not just analog data. And we're going to, we've been working on this project for quite a bit, and I'm coming back to it. It's been about a month since I last spent good time on it, but over the weekend, I did quite a bit of hacking and got very far. Actually, last week, we were showing off using the eval board version of this chip, the ATSAMR 21, and we were using it to debug and decode the data coming out of this Philips Hue tap. Remember, we took this apart, figured out it doesn't have a battery, but it has a ATMEL ATSAMR 86233 radio inside of it. When you press the button, it generates just enough energy to transmit a small 802.15.4 or Zigbee packet. And I had this set up as a sniffer, and I'm going to show actually kind of how I did that, because I sort of cheated by saying, oh yeah, your sniffer's done. But tonight, let's talk a little bit about doing the bring up for this ATSAMR. Last we just worked on this eval board, but now it's time to go to the final design. So let's go to the overhead. I'm going to show off some fun things on the hover cam. Okay, so this is that eval board that we were working with before. And this is from ATMEL. It's the ATSAMR Explained. This is the ATSAMR itself. This chip contains an ATSAMD 21, which is an ARM Cortex M0 Plus processor, quarter K of flash, 32K of RAM, 48 megahertz clock, DMA, all that good stuff. And it also, over here, has in the same die an AT86RF 233 radio. So it's a 2-in-1 chip. It's got that Cortex core, M0 Cortex core, and a radio core. And so this section over here, you can tell is the radio section, because this is where the Balun, I don't know how to pronounce Balun. Is it Balun or Balun? I think probably it's Balun, because balanced, unbalanced, input, output. Well, we'll find out. So yeah, just so I have to hang it with more RF engineers. And then it goes out to this analog switch, and then we've got a chip antenna or an SMA antenna. On the back, there's an eDebug debugging interface, SWD, programming and debugging. So you can use this with ATMEL Studio if you want to program it directly. So this is really nice to kind of get started and play with this chip. It's got everything on it. ATMEL's done a really nice job with the Explained series. I really like them quite a bit. Great for getting started with a chip. And we did get this up and running. I think last I checked, I think we got the bootloader, and I think we got an LED blinking, which basically means, once you got the bootloader going, now you can really go whole hog, get Arduino IDE working with it. And this is the final design, or the Rev A of the final design. It's going to be a feather format, micro USB with battery charging for portable LiPoly. This is the 3.3 volt regulator, LiPoly charger, little protection diode, all these pins broken out, analog, digital, SPI, I2C, serial UART. And this is that ATSAMR. Same chip, but over here on the right, two crystals. There's a 32 kilohertz crystal for the M0 core and a 16 megahertz crystal for the radio core. There's two separate crystals. It might be possible, because it looks like inside, the radio actually does do a divide by 16 and pushes the 1 megahertz clock out to a pin. So it might be possible to have the M0 clocked off of that. But since the bootloader and the Arduino M0 core expects there to be a real-time clock crystal, we just decided, hey, you know what, for 30 cents, it's worth it. Let's just toss that on there. Might be handy for low power mode. You could put the radio to sleep and then clock the M0 very slowly. And then we have the analog front end for the radio. In this case, we had two decoupling capacitors for the RF. Turns out that the Balun doesn't actually require it. I think we looked up the wrong data sheet or something. So I just replaced these with some wire. This Pi network isn't required. because we're just beta testing. I'm not making sure that, I'm pretty sure that the antenna wouldn't need it anyways, but I just shorted it out. And then we've got a 2.4 gigahertz chip antenna with the balun. And what's interesting is the balun is actually designed specifically for that chip. So this part number 2450BM15A0015E, there's like a whole series, like 25 of these baluns. And this one is for the AT86RF 232, 233. It says ATMEGA 256 because it's there's a chip that instead of the Cortex M0 has an ATMEGA 256. But these little ceramics are really handy. And I actually don't know that much about balanced versus unbalanced output. I mean, I understand that you need to convert one to the other using a network. But what I think it is when you have a balanced output, you have opposite sine waves. So basically, you know, if you've ever done like bridge tide load, or you've driven a piezo by alternating a pin, like differentially, I think it's kind of like that. You basically have two RF outputs and they're differential, and so you get a little bit more gain that way because your sine wave is basically twice as high because you use the inductor to balance that out, so you get like a twice as high sine wave. But we should probably check that out in the ARL handbook when I get a chance. But this little chip does all that for you. So it has all the ceramics, it's tuned. The output of this chip is 100 ohms, so this impedance matches just everything for you. Do you need to use this? No. You could do it with individual 0603 or 0402 components. But you know what? For the price and the size and the fact that this just works, you're best off going with Johansen. Johansen makes some really nice baluns. They're the makers of not only these baluns, but also the chip antenna. So nice people, Johansen. Or Johansen, I don't know. They have like a Viking ship as a logo. Goes well with the an ocean dolphin. Maybe they can ply the seas together. Okay, so we did get this working, and we created that bootloader. So now we have to get the bootloader onto this feather. And on the bottom, I've got the two pads, the SWD clock, SWD IO. I could probably have put a JTAG connector or an SWD connector, but I'm kind of lazy. And also, all of the feathers use these two pads in these locations. So I have a general purpose jig that I made. General purpose jig. Bring out the general purpose jig. So I got my J-Link. General purpose stands for J-Link. And the J-Link cable comes out here, goes to a little SWD adapter. I know this is kind of, I didn't need to have so many adapters, but this is kind of what I got. I'll take this ISP adapter out, so it won't be confusing. So the SWD connector, you know, it's that 0.05 pitch connector, goes to this breakout which has all the pads labeled, so VREF, ground, SWDIO, and SW clock. And then I have this little jig that I just made, and it has pogo pins that align with, does it go this way? Yeah, I think it goes this way. So it aligns so that these two pogos over here touch the SW clock and SWD data. And then also has 3-volt ground reset. There's also a couple other pads because this jig is multi-purpose. I use it also to program the 32U4 based feathers. Anyways, so I can just hold this in place while I program it to program in the bootloader. So put that in. And then let's go to the compy. So my compy, if I run ATMEL Studio, this is one of the nice things about having all the feathers use a very similar chipset, 32U4 or the ATSAM D21 series, is once you get used to the tool chain, like it's one of those things where it's like, oh my God, Cortex M0 is so difficult, so complicated, so different, until you get used to it and you're like, oh, I just understand how you program it, I understand how you debug it, I understand how the bootloader works. It's just a familiarity that I'm getting a little bit closer to. So under device programming, it automatically detects my J-Link, and I know that I'm doing an ATSAMR because that was the last thing I did, so you select that. And then while holding down the board, can you go to triple view?
Yeah, you want to do.
Yeah, so you can see it right. So holding down the board, let's see, make sure I kind of get it nice and red. I click read signature, and it reads the signature, so that means it's connected. And then I have that bootloader that I programmed, I compiled last time, if you remember. Program it in. Uh-oh. I think I jiggled the wire. Ooh, that's cool. I totally crashed it. Hey. No? Oh man, it's so over. Hold on. Let me unplug my J-Link. Oh, my J-Link cable's loose. That's no good. Yeah, it's totally freaking. That's cool. It didn't crash. It actually said, hey. J-Link disconnected. Try again. Okay. Apply. Ooh. I gotta start over. Doesn't like it. This is one of the trade-offs of using like handheld jigs is if you wiggle it, sometimes it loses connection and it's like, I don't understand what you just did to me. Okay. All right, we're back. So this time, be a little more careful. See if it can, I hope I didn't break the chip. Oh, did I break the chip? Hold on. Come on, okay. Great. And then program, okay. Whew. This time it worked. So you just have to hold it in the super happy way. And then I've got that pulsing red LED that says, okay, the bootloader's been programmed. Okay, so that's where you go to get your chip programmed. Okay, so the chip is programmed. I got the bootloader ready to go. Okay, so now that you've got the bootloader, and I could program it, I recompiled the BOSSEC tool so that it could talk to the SAMR. And the next thing you have to do is you have to make a new variant, basically, for the ATSAMR. Because the ATSAMR was just a little bit different with the way the pinouts worked out. Like not every, even though it's an ATSAM-D plus this radio, not all the pins are available. So I basically copied Arduino 0 into a new folder called 0 Radio. And pretty much all the work you have to do is in variant.cpp. So this file, which is extremely large, dictates all of the pins that are available. And what's interesting is if you look at the ATSAMR data sheet, if you look at the pinout, let's see if I can find the diagram. Give me a second to find this. Oh, here it is. Hide. Widen. Okay. Actually, shrink this. So this is the entire chip. Oh, can you go to just computer? Thanks. So this is the entire chip, and it has even all the pinouts, and she'll say, hey, this is the front end. So this is the radio, and this is like AT86RF233, and over here is the core itself, the ATSAM D21, and again, it's 2 dies. Like it isn't one chip, it's 2 separate chips, and they plunked them into the same piece of epoxy, and then they ran bonding wires. Maybe I'll get some acid, we can drop acid on this and show that there's 2 actually chips inside of it. The AT86RF233, it's connected to these pins over here. And some of these are shared, like the ground is shared and the VDDIO is shared. And then this ATSAM-D core, there's a couple of wires that are only internally connected. So PC18, PC19, PB30, PB31, PB00, these pins are internally connected to the SPI and the control logic. So PB15, which I think was normally like digital 3 or something on the Arduino, is not available on this variant because it's used internally. Like you can't have, I mean, you should use it, but like you can't have it be like available for general purpose use. You want to make sure that it's kind of, it's relinquished and allowed to use for the radio control, so that you don't have the user accidentally like you try to use this SIRCOM or something which would break the radio connectivity. And this is that clock pin if you want to get a 1 megahertz clock back out. So when we take the variant and we set it up, like for example, port A11 and port A10, which normally would be pin 0 and 1 on the Arduino 0, if you look at the data sheet, these pins are used for, 10 and 11, hold on, PA10. Yeah, so these internal pins, they're not available to be like configured with. Instead, like they're used for the RF control. So you want to make sure that you just like notify yourself, like, okay, these pins, they're used for the digital 4 and digital 5 control. And then some pins like PA21 don't even appear. So PA21, for example, was a pin that was used in the SAMD as 2, 3, 4, 5, 6, pin 7. But if you look through the data sheet, it doesn't even appear. Like it's not in existence. You actually, I think the register is there for that pin, but if the header file for it will not let you actually use it. Like it'll say like, hey, that pin's not available. So instead of trying to reassign that pin, I actually just removed the setting from the variant data. Like I just left this blank. So if you try to use pin 7, like nothing will happen. And then a bunch of other pins are not available. PA02, PA08, PA09, these are not available. So these analog pins also are not around. So A0, A1, A2, those are not going to be available for user projects. So you have to just make sure that when you document how to use this chip, they can't use those. And then there's a couple other things like the SIRCOM. We actually had a whole video on SIRCOMs and a tutorial on SIRCOMs. That's the serial communications module that lets you use SPI, UART, or I2C. SIRCOM 4 is basically internally dedicated. So SIRCOM 4. Let's go previous.
Maybe on computer for a bit?
Yeah, I think you can later.
Yeah, I'll be back in a minute.
Yeah. Let me see if I can find. Yeah. So SIRCOM 4 is dedicated. So you want to make sure that SIRCOM 4 isn't normally used because you can have the SIRCOM, that module, go to different pins. So you just kind of have to like noodle with the variant. And like I'm not going to go through the whole details of how I changed it on the variant file. Like I2C ended up being on the same SIRCOM. That didn't change. But the hardware serial actually did. So the default serial, I had to change the pin outs to be on like different pins, and you can rearrange what they are. And so SPI is no longer on SIRCOM 4; it's now on SIRCOM 2, and UART is no longer on SIRCOM 0; it's on SIRCOM 5. So you just kind of have to tweak things around. And in the end, there's actually pins that don't exist on the SAMD that do exist on the SAMR. These are all the control pins. Like these are not used normally on the ATSAMD. PB00 doesn't even exist in the data sheet. Neither does PC18 or PC19, which is kind of interesting. Like they removed some pins, but then they created other pins under different names. So we added these at the end. So this is, also there's no DAC, which is a little sad. They took out the DAC. I would have liked to have that, but maybe there's no space for it. I don't know. So the DAC, pin 42 and pin 43 are blank. They don't exist. But 44 through 50 do exist, and there are these special pins, PB15, PC16, basically all these other pins. And they're just used as GPIO, or in the case of these four, they're SIRCOM for the SPI that communicates with the radio. And it's just like it's a little bit different than an 8-bit processor where it's like there is one pin that's used for SPI, or there's one pin that's used for I2C, and it's like if that pin's available, that pin's available. If it isn't, it isn't. With the variance file in the Cortex M0, things are just a lot more flexible. If one pin isn't available, you can always move that signal to another pin. There's a lot of alternative locations, which is kind of nice because it turns out that you can, even with the pins that are missing, you can rearrange the rest of them to get all the functionality you want. We still have a serial console. It's on Circom 5 because, again, Circom 0 is no longer in existence. And what's interesting is the variant H is pretty much the same. A couple of the pin definitions changed, like the analog pins are different. And then over here, I created a definition set for all those internal pins. So the reset pin, the clock pin, the sleep transition pin, clock, MISO, MOSI, select, and IRQ. Those have Arduino pin numbers because I created those pins at the bottom, so 44 through 50. And, fix the Circom 1 for serial 1. And then there are two SPIs. So you can have SPI 0, which is the default SPI, and that's used for like if you want to control an OLED, or you want to control a TFT, or you have some other SPI device. But I also create SPI 1, which is the internal SPI device that is used to communicate between that Cortex M0 and the radio. So you define the pins, and then you basically, the Circom tutorial where you set up the SPI pads and tell it which pins and which peripheral, you define this here. And then what's neat is the Arduino core actually creates the variant for you. It creates the SPI device for you. So now you have SPI 0 and SPI 1. And SPI 1 is just for talking to the radio. So that's kind of nice. It's very elegant. So instead of like having to hard code it as like, bit bang or something, you actually have a proper hardware SPI interface. So let's see. So we've got, is there any questions? I know you're back.
No.
Okay, great. So once we have that set up, you can actually, this is an example from Max Dewey G. Sens. Thanks. This is a demo for the AT86RF233. But what I've done is, instead of having it be an external chip, of course, this demo was designed for like you have a breakout for the processor and a breakout for the radio, but I can actually kind of smush them together just by using SPI1. SPI1 now is my way to talk to the radio. So I can set up this SPI, and then the pins that are used for the radio are just pins. I just set them as input, as outputs. They're already defined for me, and they're not exposed, but as far as the core is concerned, they're still bonded to the chip inside. And this demo is kind of cute. What it does is it turns on the radio and sets it to be in promiscuous mode, which means that the radio is on and just listening. And every single packet, even if it's not addressed to this radio, because each radio has its own MAC address basically, and it has its own PAN, the personal area network, and the personal area address and all that stuff. You can make it so it only looks for packets that are directed at it, but if you put on promiscuous mode, you're listening for everything. So this is common with Ethernet if you want to sniff Ethernet. Wi-Fi a little bit tougher because there's a lot of encryption. But what's nice about Zigbee is a lot of stuff isn't encrypted over Zigbee, so you can have a lot of fun sniffing it. So this basically just writes the registers. If you look in this data sheet, that basically says you can use promiscuous mode, and then compliant scenarios. And then, it basically says like, hey, here's how you do it. Set address 17, register bit to 1, set register 2E, bit 4 to acknowledge, And if we go here, we'll see, yeah, that's what we did. We've got that promiscuous mode bit set and this disac bit set. And then you just tell it which channel you want to sniff. So there's channels 11 through 25. Each one is a 5 megahertz offset. I think channel 11 is 2405, and then you add 5 megahertz per. The Zigbee is divided into a set number of channels. And you kind of have to decide which channel you want to sniff. You can't sniff all of them. It can only tune into one band. So you have to decide which channel. And then you can just loop through and just ask it, essentially, hey, have we received an interrupt telling us that a transmission, we have finished receiving a transmission? If so, print out the frame size and the buffer. Very straightforward. I mean, there's a lot more code here just basically to handle the state, but essentially you just listen for frames in promiscuous mode and then you print them out. So what's neat is because the bootloader is Arduino compatible and I got all this stuff working, I should be able to just upload this code. And it'll show up as a comm device, and now it's sniffing. So listening on channel 11, frequency 2405, and it just gives me some data. And this is just a once a second report, just tells me like, okay, like what's going on. And then this device is transmitting on channel 11, so when I press the button, I get frame packets. So here you go, like packets O data. Whee! So every time I press it, more packets. Lovely. So we're close to a really awesome sniffer, but what would be really neat is if we could take this and open it up or stream it in Wireshark, which is a very nice, extremely old at this point, well-developed sniffer application. It was designed originally for Ethernet, and then Wi-Fi, but you can, with a little bit of noodling, get it to work with any protocol such as this. And the way you do that is you do Wireshark named pipes. You can see I read this. So normally it would open up your Ethernet device, would open up your Wi-Fi device, and it would sniff the packets directly on that device that's connected to your computer. But if your computer doesn't have a Zigbee chip in it, which most don't, you need to have this external hardware that would listen for those packets. Even though it's on the same frequency as Wi-Fi, your Wi-Fi device is not set up to look for Zigbee. So what you have to do is you have to basically tell Wireshark, hey, I have this pipe, I have this, it's not a file, it's kind of like a file holder. Basically, like you can write to the file and then the other device will read from the file, but there's no actual storage going on. It just, the data goes from one application to another. Have the ATSAMR sniff the packets, send it through serial, and then have a program that listens to serial packets and then outputs that to a file that Wireshark then reads. And so there's a couple little hops, but if you do this properly, Wireshark just thinks like, hey, I've got packets coming to me from this device, which is actually a named pipe. Turns out it's not too hard under Linux, but it's a kind of a pain in the ass under Windows. So you have to install Python and Py-Win32, but once you do that, it's not too bad. So you do have to have the output be in a binary format, which we'll do that in a little bit. And I actually ended up modifying this program by Matijas Kujiman. I'm sorry, I'm not pronouncing your name correctly. But he wrote something that works for Mac and Linux. And I'm like, okay, well, I'll modify this to add support for Windows. So under Windows, you create a named pipe. And I guess pipes exist under Win32, which is great. It goes into //pipe Wireshark. And then you open up Wireshark. Hold on, let me see where it is. You open up Wireshark and tell it, read from this pipe. So this is like the -i, read from this pipe file. create the pipe, wait 5 seconds for the Wireshark to open, and then you basically just have to write a header telling it what kind of data it is. Like in this case, it's 802.15.4. There's some magic number. You have to send it just to tell it, hey, this is proper Wireshark data. And then for every packet, you send it the timestamp, the timestamp in seconds, the timestamp in microseconds, the length of the data, and the actual data itself. Sorry, number of octets. I guess you send it twice. And then you send, because you can send multiple packets. So you send it the packet length again, and then the data from the packet. Okay, so the only difference is to make this compatible, I had to make a slight modification to this program. While this program is very nice and outputs lovely hex data, that's not the format that the script wants. The script wants the packets to be in a binary format. So we have a version called PCAP, and this version will, when you print out the packets, get to the packet printer, when you receive a packet, it will use serial write to write the binary value of the frame length rather than this human readable text. And then it will write the raw byte of each frame buffer rather than printing it out in a lovely hex format. It'll actually write the binary data out. So let's upload this. So we've got one version that's like human readable, and then we're going to have a version that's machine readable. I mean, you could make the Python script read the human readable, but it's like a lot more parsing, and it's a lot easier just to fix it on this side. And then to read the data, just to show you the format, I'm actually going to use XCTU because the Arduino serial console is a lovely serial console, but it does not show binary data very well. So here is the binary packet data, and in hex, it's streaming all the hex data direct. So this is basically a direct pipe from Zigbee to serial. Basically, that's all I've made is a direct pipe connection. Except before each packet, it also prints out the size. Oh, and the reason there's so much data is actually I'm sniffing on port channel 25, which is extremely busy. But I'm going to change that back to 11 to make it a little easier to see what's going on. Let's compile, load. Sometimes I got to kick the bootloader. I'm not sure. I think it doesn't like it. XCTU is opened. Okay, so this time it's much quick. I just print out sniff at the beginning to tell it, like, hey, I've launched. And then if I press this button, I get a packet. And you get like the size of the packet and then the packet itself. So this is a lot easier to see than the big stream. Again, you have to sniff on every channel and see which channel has the most traffic, and this house traffic is all on channel 25. Okay, so now that we have that, we're going to run that script that listens on serial COM port 3. And I'll get rid of this delay, that's not necessary. And it's actually going to, sorry, I got to reset. Yeah, no, it's gone. Let me try again. Whoa, that was not right. CD, C, users, Dropbox, RF. Okay, yeah, this site totally crashed. All right, well, let's try in this window. Python. Reset. Okay. So this actually launches Wireshark because that's to tell it, like, hey, open up that name pipe. And now it's just waiting. And Wireshark is also waiting. So there's that name pipe that they're communicating between. So I've got my Hue tap. I press it. And it's like, hey, I got a message. And what's nice about using Wireshark is instead of just like, 01, 08, 17, FFFF. It actually decodes it in a very nice, handy way. So it tells you, this is a broadcast. It's a sequence. There's a sequence number to it. It tells me the address very nicely. It tells me, okay, the checksum is correct. And then it has like all sorts of details of like the security frame counter and then the command. So it's scene 0. And then if I press this one, this is like a different toggle command. Scene 2. So yeah, all sorts of different data coming out here. So it's kind of interesting. So you can look at each packet as it scrolls by. And over here it tells me like, hey, I found a packet. So that's kind of nice. You can see it's much easier to debug what is going on around you if you can get it into Wirecast because it has the parser already set up. And then what I can do is, if I want to check out that really nice and busy zone, I will change the channel in my Arduino sketch. Eventually what I can do is make it so that you can tell the sniffer what channel you want, like on the command line, by like sending it a serial command and say like, hey, tune to channel 18. But for now, I'm just hard coding it because I'm lazy. Okay, and then we'll run this again. It takes 5 seconds while it waits. And then it's just like, it's streaming crazy amounts of data because we've got so many lights in this area. So there's like all these broadcast packets and like acknowledgement packets, and then who knows what's going on here. Tons of data. Some of it's Zigbee, and some of it's just like raw 802.15.4. So yeah, this is kind of fun. So I mean, we have like 50 lights or whatever devices in the area that use Zigbee. But if you're trying to debug a particular product or device, this is very handy. So you can just like sit here and use it and then watch the packets go by. And then you can, of course, you can save it and decode it. And if you want to, you can, of course, then program it into your radio to retransmit if you want to do a replay attack. Not going to be possible with this because this has replay attack security, but for some simpler products, it might be possible. So that's what we're doing tonight. That's what we did. What do you think?
That was pretty cool.
Okay.
Okay, that was super helpful.
I hope so. Yeah.
This is a follow-up. People were asking for this before.
Yeah, this is like kind of 2 weeks worth of backlog, but got the name pipes thing working, so I thought that was neat.
Yeah.
So this is actually, what I actually did the whole sniffer thing for is actually just to test the hardware. I'm actually not, there's nothing in here that I might sniff stuff and then do some analysis, but what I was really interested in was this working? And if you can get packets coming out, that means it's at least able to read. And then when I get another one of these built up and programmed, and I can have it send and receive packets back and forth, I can have a third one listening in. So these are it's very handy just doing development for Zigbee to have a sniffer, because it's just like really, like you're not going to be able to like oscilloscope your 2.4 gigahertz packets. You can't do that. So instead, having one of these listening in makes it really easy, like, sending a data, the data packet, is it correct? Did the checksum, did you do that correctly? And if you're getting a lot of errors, you're like, okay, maybe there's something wrong with my radio.
Yeah, I feel like in our world of hobbyists, there's certainly no one talking about this, and that's why there's not a ton of hardware, because this is like the dark arts here. Like, you thought a toolchain was hard to set up?
Yeah.
Okay, well, guess what? Now you're going to be like doing sniffers and all these other things.
Mm-hmm.
So, okay.
Yeah, actually, can I show this last thing as a
You can always show this last thing. It's your show.
Yeah, well, it's
do
a
whatever you
little
want.
weird.
I'm just here.
So I actually bought this because I was reading, before I got this up and running, and I was like, well, I should, while I'm developing with this eval board, I should get some sort of sniffer. I didn't realize how easy it was to make a sniffer. It was pretty straightforward using some nice example code. But I got this, which is really cool. This is like some sort of like evil shrimp.
When I first saw it, I thought it was a graphic from
Razor,
it was before it was called anime. It was Heavy Metal was a cartoon that was like an adult cartoon that had Yeah, that had like creatures that look like this.
Yeah,
so-
this is like super metal.
Yeah,
And like they got
Atmel
the
if
red
they
spot
did that
color.
more. Yeah, I wish Atmel made all their packaging look like
So this is like the gothiest, most metal
yeah.
of devices, and this is basically a tool that you can use for sniffing. Turns out actually doesn't come with the sniffer firmware on it, and so you have to like solder on a JTAG, and I was like, oh my god, this gets so complicated. It was actually ended up being like so much more work than just. I ended up saying like, you know what, I'm just gonna try to make even though I didn't know that this hardware worked, I was like, I'll just try getting this to run as a promiscuous mode. It turns out it was quite simple, but this is a separate chips. This is an ATSAMR 233 and an AT90 USB 128.7. So it's kind of a predecessor of the M0. This is like a gigantic crystal. This crystal's huge. Like, what's going on here? And they have this.
I like that the little logos on the back of the
Yeah, I don't even know what this thing is. It's a little scary. It's like a metallic. It's like a robo. And then here it really looks like a shrimp because it doesn't have the
Yeah.
legs. Anyways, you can tell that there was just some like Norwegian death metal fan.
It's like an alternative.
at
It's
Atmel.
like a parallel universe AVR, where like we're running AVR, and this is our Feather series.
Yeah, but this is metal feather.
Yeah.
So I didn't end up using this, but that's okay. I mean, I might eventually, but I was like, oh, I actually don't have one of these through-hole connectors. And I was like, I could solder wires, and before you know it, you're like, I'm spending 2 hours like shaving this yak. So that's why I ended up not using this. But I wanted to show it off because it's totally metal. So metal. And that's what I have to show for today. So we're going to be doing, I'll probably do point-to-point 802.15.4. Or maybe I'll get some XBs and we'll sniff those because the XBs are definitely,
Yeah.
those are for sure 802.15.4, which are going to be compatible.
Which XB you think you're gonna do?
I don't know, Series 1 or something maybe because
Yeah.
they're simple. And just see what, oh no, sorry, those are 18, they have 802.15.4 the Series 1 or 802.15.4. I think the Series 2 are Zigbee, true Zigbee. I don't remember. I don't even think anyone who works at XB
Well,
probably remembers either.
They have this crazy chart that has all of the XBs. We'll pull that up when we do it, because as you know, I answered a lot of the customer support emails for a long time. For a while, like Series 1 and Series 2 was the most confusing thing because one was newer, even though it said XB Series 2, XB Series 1. So, anyways, we'll.
Oh, this is neat. Oh, can you go to the overhead? This is neat. This one has a little bit of.
You mean your computer, right?
Sorry, yeah, computer.
Yeah. What are you looking for?
So this packet actually says Philips. Like it has a MAC address. And it's like, oh, it's a Philips light.
But maybe it's me.
Oh no! Oh yeah, wait, you're right.
It's probably my
Yeah.
my laptop.
It's. Oh, you think it's actually? No, I don't know. Why would it have your MAC address? No, I'm saying it decodes it based on the MAC address. I think
Yeah, it's my lights.
it's your lights, and then yeah, it's encrypted. Ooh, severity warn.
I-
So I got to figure this out eventually.
I encrypt
Data.
my lights.
So yeah, they encrypt everything. So it's a little tough to. They do this because they don't want people to make hardware that works with it.
Yeah, other LED lights. Okay.
If only we knew the ZLL master key.
All right. Well, thank you for tuning in, Desolate Data. Tune in this week for more exciting shows. Please support Adafruit and pick up an electronic kit and more at adafruit.com. Thank you so much.
Yeah, these are the tools we make to make the tools that we make to make tools that we sell.
Tools that make tools.
Yeah, but it's handy. Actually, I don't know of any off-the-shelf Zigbee sniffer. So maybe when the Feather gets released, maybe we'll make a version that already has the Zigbee sniffer firmware on it, and we can sell it to.
Yeah. All right, we have to come up
Hardware
with a
hackers.
bird name like the honeysuckle.
Is that a bird?
Isn't it like a type of bird?
I thought that was a type of flower.
I'll have to look up bird names.
Okay.
I'm still obsessed with the grackle.
Grackle.
But-
We could call it the grackle.
No, there's probably some bird that can like sniff or slurp.
Sniffly bird. Maybe like a toucan. It's got a big beak. A big
Yeah.
nose.
All right, I'm sure there's.
80 toucan 15.4.
Yeah.
Okay.
Okay. Well, thanks everyone.
All right. Thanks for joining me in the Desolate Data. I'll see you soon.
Bye bye.